Donc, bonjour à tous. Je vais présenter en fait en anglais parce que je veux pratiquer un peu plus la présentation pour la prochaine semaine. So my colleagues already described what the standing column well system is. I just wanted to say that here the groundwater is actually like reinjected and re-extracted from the wells, and so it is recirculated between a heat exchanger and the standing column wells multiple times. This means that when during a heating season, the groundwater will get colder and colder. And this means that a certain point will be the risk that the groundwater can approach freezing conditions. And to avoid this, usually the pumping flow rate is kept like high to avoid this. But this will mean that the pumps will also consume a lot of energy. So here we also want to try to limit this pumping energy and to try to save energy and to increase the energy efficiency of the system. So here on the right, you see that for example, for a standing column well system, the electrical energy usage of pumps is quite high. I've highlighted the submersible pumps and the groundwater pumps. It is composed like a consistent part of the total electric consumption. And then I also highlighted the electric boiler that is in black there, because usually that if the pumping pumping management is not is not done as it should, like it's not done correctly, then the electric boiler can intervene to save the groundwater from freezing. And this is particularly bad because the electric boiler has electric peaks in the consumption that are way higher than the heat pumps. So for example, here in blue, you see that there's a heat pump consumption, and in orange, the boiler. And the boiler consumption is actually like something like 4 times more. And this is particularly a problem in Quebec, where for institutional buildings and commercial buildings, the electricity pricing scheme is penalize a lot the peak demands. So for example, for each month, there is about $16 that is applied to each kilowatt of the maximum peak demand. And in this also this type of billing, the maximum winter electric peak will be also applied for the rest of the year. So this can adapt to the usage of the boiler can cause dozens of thousands of dollars of bill more than just use the heat pump. So let's talk about the pumping control strategies that there are. So until now, for standing column wells, they've been implemented a type of control strategy that is called reactive. This means that the flow rate is controlled depending on the current state of the system, so on the current measurements. But this can bring to a delayed response, meaning that the system will react a little bit too late, and that is problematic on handling peaks, demand peaks. What I'm proposing here is to use predictive control strategy. When a predictive control strategy will try to adjust the controls depending on the future state of the system. So this is kind of a novelty for standing column wells, and predictive control managed will allow to have an anticipated response, meaning that you can handle peaks better. So here in this work, I try to explore the potential predictive control through something that we call heuristic predictive control. This just means that I took a model, a quite accurate model of the system, and I reiterated it multiple times until I found an optimal pumping profile. So this is not really a control system that is realistic and can be implemented, but we can try to understand from this optimal pattern that we obtain. We can try to understand what are the possible rules and possible type of controls that we can apply in the system in a more easy way. So we can try to deduce some rules and then use them more easily in the school. So the case study I worked on is called École Clé des Champs. Is a school in the north of Montreal where there's been recently renovated from a fuel oil boiler system to a fine standing column wells HVAC system. So here you have the schematic, and I want to go into details now, but I can show you that here there are also two water to air heat pumps that I didn't really consider after in the model, and I just integrated them into the water to water heat pump. And there are two ways to distribute the heat in the building, that is for ventilation and for hydronic heating. So my methodology is basically made up by two parts. On the first part, I went through the modeling of the system, so the model of the building, of the heating, ventilation, and air conditioning system, and of the ground. So the ground is the ground model is made through a MATLAB connection. The second part instead is mostly related to the control. So first I went through the predictive heuristic optimization that I will show you later on how it's made. And then I try to identify simple rules that can be implemented in the building to reproduce similar performances. So talking about the building model, I went through a 3D model first. Then I tried to collect all the structural data I could of the roof, of the walls, and other parts of the building, analyzing the thermal capacity and the thermal transmittance, that is called the U value. And then I try to do a characterization of the heat gains and of the heating and ventilation parameters of the building and all the schedules. Then I set up the model in Transit, that is an energy simulation tool, with 23 thermal zones. So here we have an overall overview of my heating, ventilation, air conditioning model. So it's divided into multiple loops, and I will just try to show here first the ground loop. So you can see that the standing column well, it's a block that is represent a connection between MATLAB and Transys. In MATLAB, there is a non-stationary convolution algorithm that is run that uses 49 transfer functions. Here you have the control blocks of the system. So on the left, there is the freezing control component. This one will activate the boiler in case the groundwater will get too cold. So for example, if you consider the water that goes from the heat exchanger to the standing column well, it's called leading water temperature. If this goes below 2 degrees Celsius, then the boiler will be activated automatically. On the right, instead you have the heat pump control. This one will switch off and on the heat pump depending on the return water temperature from the building. Here you have the collectors that will manage all the flow rates throughout the building and the HVAC system. And here on the right, there are the heating distribution system. So there is a block there that is representing the air handling unit, AHU, and the convectors that are the hydronic heating. And both of these are connected onto the building to distribute the heat. So here I will try to explain you what is this heuristic predictive strategy. So I will first start focusing on the table on the right. So we have 5 levels of pumping that I will apply, starting from a first level in which the pumping is at the minimum at 200 liters per minute, and the bleed is at 0. Then this will gradually gradually increase throughout the levels until there is 600 liters per minute of pumping and 90 of bleed. This 90 liters per minute of bleed have been identified as the threshold to avoid injection well flooding in this system. A 5th level there, it's that is indicated as 10 hours. It's because this 5th level will pre-pump, so means that we start to pump earlier on than the other levels. So the first step here is to simulate first the first level, just minimum pumping. Then I will calculate here at step 2 a binary variable that I call warn, because it's like a warning, when the living water temperature of the groundwater will go below 4 degrees. So for example, on the right, you see the blue line and the red arrows. So when the temperature of the water will go below 4 degrees, this binary variable in red, it's set to 1, and it will stay 1 as long as the water is below 4 degrees. Then the third step, I identified a binary variable called act there in black. This will try to anticipate the warning of 90 minutes. So the value of here 90 minutes is just that I found that this value that is suitable for my study case, but then it can vary from study case to study case. Oh, okay. Okay. Yeah. So once I calculated this active variable in black that is anticipating the warning, then this variable is then printed in a CSV file and will be used on the next simulation to increase the pumping level from 1 to 2. And then these whole 4 steps are repeated on and on until I have all the 5 levels I presented to you before. So once this process is finished, you will have something like on the right, in this graph on the right, you will see the blue line. That is the optimized pumping profile over 2 weeks. So what I try to do here is to compare this profile, this optimized pattern, compared to the external temperature and the type of occupancy there is in the building, here represented by the indoor temperature. So to see if the building is occupied or not. So here I try to understand, depending on the external temperature that you have and the type of occupancy, which are the rules, simple rules that you can apply to try to reproduce this predictive strategy. So what I identify, for example, is that during the weekdays, it's very important to increase the pumping rate during the night. So, for example, from 3 a.m. to 11 a.m. And do this depending on the external temperature that is measured during the night. That is very important. And then I also found out that the Mondays, or in general days that are after holidays, will be more tricky because they come after a period that is colder. So the building gets colder, and then it will require more power to get activated. So it will require a little bit more extra pumping, so pumping earlier and more. In fact, during the weekends, I just noticed that there is no need to really pre-pump a lot, and you can just adjust the pumping depending on the external temperature. Then I also noticed that below certain external temperature, like when it's really cold, below minus 20 degrees, it's really necessary to pump up at the maximum. So here I have the results. I tried to compare this heuristic predictive control and the rule-based predictive control against 3 reference scenarios. So as references, I put a scenario in which you keep the pumping at the maximum, but bleed at 0. Then the minimum, which you have a minimum pumping, so we use a boiler quite a lot. And then a reactive type of control, which you can keep the heat exchanger temperature difference at 2 degrees, and the bleed is managed for a bleed for dead band control. So here you will see that the main difference will be in the graphics on the center. So here I will remind also that this is calculated on a monthly base on a very cold winter, a very cold year, with a daily temperature of minus 20, minus 26. So here we have the maximum power that is very clear. The difference here, the reactive control will use the boiler as well as the minimum scenario, but instead the predictive and the rule-based predictive will not use it, and we keep the power down. Then you will see on the left the energy use instead, where the reactive control as shown to be the most energy efficient, but the predictive control and rule-based predictive are quite close. So I have a good energy performance, and also compared to maximum and minimum scenarios. So this difference between the scenarios can be also seen in the costs, the total cost here on the right. So you will see that the predictive both predictive control and rule-based predictive will have the lower costs of all the scenarios. This is because the boiler is not used, and also there is less usage of energy compared to the max scenario. Here I just wanted to show some simulation results. So just here, for example, on the 3rd row in green, you can see the pumping profile. And on the left, you have a reactive scenario, and on the right, a predictive scenario. So when you have a reactive, you will see that the pumping will increase quite late, when it's already quite late, and this will activate the boiler in red, and it will cause huge power peaks. Instead of the right, you see that the pumping on the 3rd row will increase earlier on, and that will prevent the system to using the boiler. So as to conclude, I managed to obtain a 5-level heuristic pumping predictive strategy that is minimizing the maximum power, but while also having a good energy performance compared to reference scenarios. Total costs compared to all the other scenarios are minimized. So before the difference in the graph were like $2,000 to $3,000, but that was only 1 month. And if you count that the peak demand is billed for each month of the year, then this can add up to dozens of thousands of dollars. So I estimated around $16,000 of difference. And then as a third point, yeah, the energy usage is being quite it's quite reduced compared, for example, to a maximum scenario in which you keep the always maximum pumping. And I also tried to take this predictive strategy that was quite ideal and to identify some rules that can be easily implementable in the systems. And also this type of strategy as showed to be have a good performance. As of some future work, I already worked on, I don't know what happened here, sorry. So as a future work here, I will try to, I will already worked on, and I will try to finish that work soon, about the full model predictive control. So you have like, well, a model that will be used to optimize the control actions beforehand. This is a systematic optimization and predictive control. If you have any questions, I don't know why here is switching automatically.